Right. So you wanted me to solve self-exponential slash logarithmic equations.
That's right.
We did some of them together, such as this one where you just gave me this. So when we got here, God, can I see that? Oh, backwards.
As long as it. Okay.
Oh, it is mirrored. Oh.
I think it's fine because I've already seen it, so I think it's just to jog my memory that you've done everything, and we can always I think there's a way to flip it, we can. Edit it later. Yeah.
So we talked about this.
Yeah.
How when there's nothing here to insinuate what it's being logged by, this is automatically by 10.
Good. Yes.
So that basically I guess leaves really out and all that. So it just turns into 3x equals 10 to the power 1.
Exactly. Good. Yes.
Which is just 3x 10 equals 10. And we didn't go farther than saying that x is equal to 10 over 3.
All right.
Which I'm pretty sure is a repeat number.
Yep. What would that be? 3. It would be 3.33 repeats.
Yeah.
Good. Okay. So you got you take 10 to the power of that exponent in order to undo it. Yes.
So what's the next one? It was what I had was this.
Right.
So what I first did was I turned this into logs.
Great.
And then I moved this so it was
Yeah.
So then I went along and turned it into that.
All right.
And then I ended up, the answer I got from this was 2.99.
Right.
Which, since it's plus 1 and we want to find x, I subtracted 1.
Right.
Which that equals 1.99. Then we just had to divide that by 3.
Yeah.
To get the answer of what x is. And that gave me 0.66 for x.
All right. Nice. Cool. I'm gonna ask an extension question. So you used a log identity there, where there was an exponent inside the logarithm, and so you could multiply that outside the logarithm. Do you remember the other two logarithmic identities? There was a set of 3, and that was one of them. Oh yeah, and you came reference your notes. That's what your notes are for.
say can or can't?
You can, yeah. That's why I emphasize note taking so much.
Log b xy equals log b x plus log by.
Right, so multiplication inside the log turns into two logs adding.
Yeah.
Yeah.
And then log b times x over y equals log b x minus log by.
That's right.
And then log b x to the power of y equals y times log b x.
Good. Yeah. Just want to make sure you have all your identities.
Yeah.
All right.
That was that one anyway.
Yeah. So what's next?
On to the word problem.
All right.
Oh, I got this one surprisingly
Yeah, we're gonna do some banking, right?
easily. I got
Yeah.
this one. So it says you put $15,000 into an account that pays 7% annual interest, compounded continuously. We got rid of compounded
That's
continuously.
right. Yeah.
So
Annually.
how long will it be before you have $2,000 in your account? So in this case, A, well, lowercase a,
Mm,
would be equal to 15,000,
good.
and R, which is 7%, would be equal to 0.07,
Mm-hmm.
and capital A is 2,000. We want to find T,
Right.
so we don't know what T is. So first thing I did was I put it into the equation sequence, or sequence, the
Yeah.
equation, the equation
Formula.
That got me 2,000 equals 15,000 times 1 plus 0.07 T.
Right.
And then we couldn't just have that,
Mhm.
so it was converted into 2,000 over 1,500
Right.
equals 1.07 T.
Mm-hmm.
But that would be 1.3 repeating equals 1.07 T. And from this, we would just do a logarithmic equation.
That's right. Yeah.
So it would turn to, I would first do log 1.3. I didn't continuously do the repeating sign.
Yeah.
1.3.
That's why it's something like I would probably use 4/3
Yeah.
for a more exact, but that's fine.
So of course we can't have that in there. So it was turned into
Good. You have liberated the T.
liberated, yeah. And we can't just have that sitting there. So the next step was taking it out and doing 1.3 or log.
Yes. Yeah.
Log 1.3 over log 1.07.
Awesome.
That got That got us 3.87 for that.
Alright.
So that's T.
Great. 3.87 what? Where's our unit on that?
Years.
Yes. But it's annual interest.
Yeah. 3.87 years.
Alright.
That's what I got for that.
Cool.
And now we go on to this equation. So, this.
Alright.
Don't know what to call this.
It's called a
Geometric
you can call it
series.
a geometric series and in sigma notation.
In sigma notation.
Yeah.
Okay. So, let's reorient this.
Alright, that sounds good.
So it can easily be done.
Alright, yeah, that is the formula.
We get that, put it to the formula.
Mhm.
And then what's in the parentheses? Which gets us this.
Mhm.
And of course, what happens up here, it turns into the 3 times negative 31 is negative 91. No, 93. Negative 93. Then I finally turn this into what this down here is.
Okay.
So it's negative 93 over negative 1.
Yeah.
Which that just straight up equals 93. So
Awesome.
that's that
Yeah,
answer.
so it's to a number. Okay, let me ask you the follow-up question. So we do have a form. So this is the formula for a geometric series. But what does just the sigma notation mean? So if you were to write out the sig, because that's I call it a zip file. So how would you write that in expanded form? So the series is a sum, right? So it means something's added together.
We'd fill it in and see if it worked. No.
Elaborate.
It's basically this in reverse, but I don't think that's right. Hold on.
Yeah.
The geometric formula, which we did. Is that right? Geometric formula?
So this is the geometric formula. I guess what I'm asking, so geometric formula only works for geometric series, but sigma notation could be used for any series.
Yeah.
So what exactly? Because I guess I want to understand like the interpretation of that notation.
Do not understand.
Okay, so this is I wasn't sure if I emphasized this enough, but there's one. So basically, anytime you have a series, so basically the numbers from 1 to 5 all get plugged into here, and all of those get added together. So the expanded form of this sigma notation would be 3 times 2 to the power of 1 minus 1, which is 0, plus 3 times 2 to the 1, plus 3 times 2 to the 2, was.
Oh yeah.
And then it would terminate at 4, because 4 is 1 less than 5.
Oh yeah, yeah.
Yeah. So just never forget that a series is the sum of a
I
sequence.
just forgot what you're talking about.
It's hard to phrase the question because it's like, yes, this is you evaluated the sum correctly, but this is the expanded form of the notation.
Well, that is me teaching.
Excellent.
quotes.
Yes. No, it's good stuff.
And
And I did tell you that you needed to do that. I just wanted to see if you remember.